All right, so here is a test question that's on test number 2. I give you a sample space, and it looks like the sample space are the digits in our number system. So these are all of the digits in our number system. And then I just define event A to be the numbers 0, 1, 3, 8, 9. I have no idea why those numbers exist. This is just given information. I define event B to be the numbers 4, 5, and 6, and I define the event C to be 5, 6, 7, 8, 9. Okay, so the one question that I'm going to ask you is, and I need another index card. Hold on. The question that I'm going to ask you is, find the probability of A or B. Well, the first thing you have to do is ask yourself, is it mutually exclusive or not? So the first thing you have to do is look at event A and look at event B, and do they share any elements? Is 4 in both sets? No, it's only in this one. Is 5 in both sets? No, it's only in this one. Is 6 in both sets? No, it's only this one. So if I drew a Venn diagram, and I drew 0, 1, 2, 3, 8, 9, that would be in event A. In event B over here would be 4, 5, 6. And then 1, 2, 3, 4, 5, 6, 7 is not listed in there anywhere. 8, 9. So 7's out here. 1, 2, 3, 8, 9. 0, 1, 2, 3, 8, 9 is in this set. This set over here is over here. They don't share anything, so they're mutually exclusive. So since they're mutually exclusive, all you have to do is find the probability of A and then find the probability of set B and add them together. Okay, so there's a sample space of 10. So that's the number on bottom. My sample space is 10. How many outcomes were in event A? 1, 2, 3, 4, 5, 6. There were 6 outcomes in event A. How many outcomes were in event B? There were 3 outcomes. All you have to do is add those together and you get 9 over 10. 9 over 10 comes out to be 0.9 or 90%. Okay, now this question, find the probability of B or C. Okay, and let me turn it around. Okay, B or C. I'm going to be adding, or means add, but before I can decide, I've got to look here at B, and then I've got to look at C. Do B and C share any elements? Well, yes, they do. They share 5 and 6. 5 and 6 is in this set, and 5 and 6 is in this set. So if I drew a rectangle, in circle B would be the numbers 4, 5, and 6. That's circle B. And then in circle C, right there, there's circle C, it would be the numbers 5, 6, 7, 8, 9. And then the other numbers, 0, 1, 2, 3, are all out there somewhere. Okay, my sample space still has 10 numbers in it. My sample space still has 10 numbers, but since these two right here, since this spot right here shares these two numbers, then that means I'm going to add them. I'm going to add the probability of B to the probability of set C, but then I'm going to have to subtract out the probability of B and C. And remember, this group right here is B and C. So how many outcomes are in set B? Remember, we got a sample space of 10. So how many outcomes were in set B? There were 3. How many outcomes were in set C? There were 1, 2, 3, 4, 5. So 5 out of 10. But I've counted 5 and 6. I've counted those two outcomes twice. So I've got to take them out. So 3 plus 5 is 8. 8 minus 2 is 6 out of 10. That reduces down to 3/5. That reduces down to 0.6 or 60%. All right. So that one that's on the test, and I can't tell you how many people missed that one. I don't know, but they do. Okay, so that's it for section 3. Section 4, I copied this thing right here from page 172, and this is going to be on your formula sheet. It has the fundamental counting principle. We've used the fundamental counting principle before. Remember, that's when we did, what did we do? We did, the 4-digit code. Remember the 4-digit code? And depending on whether we could repeat or not, we had a 4-digit code. We had this times this times this times this, right? We had a 4-digit code. So we had 10 digits times 10 digits times 10 digits times 10 digits, and we would get 10,000. If they could repeat, if they couldn't repeat, it'd be 10 times 9 times 8 times 7. Okay, so that is the fundamental counting principle. The number of meal deals you can get if you go to Subway. Those are all the license plate. How many license plates can you make? Those are all examples of the fundamental counting principle. Now you need to know the difference between a permutation and a combination, okay? A permutation and a combination. Here's the only difference between the two of them, and that is whether or not order matters. So here's the easiest way for me to tell you how I remember a permutation. A permutation, when you go to the store and back in the day you had to buy locks to lock your locker at school. Most of you went to the store and you didn't want to have to keep up with a key. So if you don't want to have a key for a lock, then what do you buy? If you want a lock, but you do not want to have to keep up with a key to the lock. Well, I hope you're saying to yourself right now, I'm going to buy a combination lock. Well, that's actually not true. A permutation is an example of a combination lock. So that's the reason that the reason that I use that to remember it is because it's false advertising. There's no such thing as a combination lock. There's a such thing as a permutation lock, because when you're dealing with locks, the order of the numbers matters. So if I, and I have this on, when I graduated college 100 years ago, my mother bought me a briefcase, and the briefcase had a little spin dial of numbers. And if I chose the number 375, okay, if I chose 3 to be my first digit, 7 to be the second digit, and 5 to be the third digit, that permutation means that order matters. The 3 must be the first number, the 7 must be the second number, and the 5 must be the third number. That is a different combination than 735. Those are two different combinations. It's this using the exact same digits here, but order matters. And when order matters, you're dealing with a permutation. On a combination, 375 would be the same combination as 753. So that's why we don't call it a combination lock, because this is obviously not the same lock. But in combinations, this outcome and this outcome are considered the same outcome because order doesn't matter. And I'll give you some examples of that. It's not going to involve numbers, because anytime you're dealing with digits, that's a different that's a different outcome than that. But when you're dealing with like a committee, if you're going to pick a committee, to do something, then order doesn't matter. So that's the main difference between combination and a permutation is, does order matter? So anytime you're working any of these counting principles, okay, anytime you're working these counting principles, the first question you have to ask yourself, does order matter? Okay, so there are several different permutations here. Notice that this is a permutation. My cord got in the way. This is a permutation right here. And that notation right there in factorial, I'll show you where to find it on a calculator, or I'm pretty sure they use it on StatCrunch too. I'll show you how to find that, but I'll explain to you what that means in a minute. But here's one permutation formula. Here's a second permutation formula. And then here's a third permutation formula. So these are all three permutations. So order is going to matter all three of these, but each one of these is a different situation. And the difference in the situation is basically how many of the things that we have, how many are we going to be choosing? So this factorial, and I'll explain what that means in just a second, but this is the formula that we use when we have 5 objects and we're going to be using all 5 of them, or when we have 10 people going to the movie together and they're all going to choose a seat, versus 10 people going to the movie and only the first 3 get in. So those are like, that's the difference between I'm talking about here. We have this many objects and we're going to choose all of them and figure out how many different ways we can arrange their order. This is the formula that you use, and I will talk about this. This is a P for permutation. We have n objects and we're only going to choose a few of them. So let's say we have, I don't know, 1,000 songs in our iTunes account, or Shutterfly, or Specify, or Spoofy. I don't know what that's called, but anyway, I have 1,000 songs, but I'm going to make a playlist of only my top 10. So here I would have 1,000 songs. That's how many I have. And I'm going to make a playlist of my top 10. So I have 1,000, but I'm only going to choose 10. So this would be the formula that you use in this situation. Okay, in this situation, I call this my Mississippi. This is my Mississippi problem, and the reason that this is a Mississippi problem is because we have a whole bunch of letters up here, but but some of them are distinguishable and some of them are indistinguishable. In other words, if I pick the letter S, are you going to be able to tell if I pick this S, or if I pick this S, or if I pick this S, or if I pick this S? If we threw all of these letters in a bag, okay, let's say these are, what's that game? Scrabble. If these are all Scrabble tiles, and I threw all of these letters in a bag, and I reach in and I pull out an S, are you going to be able to tell whether it's this S, this S, this S, or this S? The answer is no, you're not going to be able to tell. You wouldn't, if I pulled out an I, you wouldn't be able to tell if I pulled out that last I or that first I, because they're indistinguishable. M is distinguishable from the letter I. You can tell the difference between the letter M and the letter I, but you can't tell the difference between this I, this I, this I, and this I. So that's what I'm talking about when I say distinguishable versus indistinguishable. Okay, because I have some indistinguishable letters, I have to alter my formula just a little bit, and I will explain that in the next video. The last thing that we come to is a combination, and a combination again is different from a permutation because order doesn't matter. Permutations are always going to have, we're going to have more permutations than we do combinations under the same event. So in other words, if I had 1,000 songs and I chose 10 of them, and then I picked a particular order. I want song 1 to play first. I want song 2 to play second. I want song 3 to play third. That's a particular order. And if I shuffled them, that would be considered a different playlist. Down here, what I'm saying is I'm going to have 1,000 songs. I'm going to pick 10 of them and then I'm going to shuffle them. And I don't care what order they're played. It's still going to be just this. It's going to be called, you know, my workout playlist. But I'm shuffling them, so I don't care about their order. Here, I care about their order. Maybe I'm, you know, it's a workout and I want to start off slow because I'm warming up, and then I want my next song to be a little bit faster, and then my next song to be a little bit faster, and then my second to the last song is going to be my wind down song, so it's going to slow down a little bit. So it's a particular order that I want, and if I change that order, I consider it a completely different playlist. So maybe I have one playlist for when I'm going on a walk with my dogs, and then if I shuffle that playlist, I'm going to shuffle it, and then it's going to be my playlist for jogging with my dogs, maybe. So does order matter? That's the difference in these two. Here it doesn't matter. Here it does. So we're going to have more outcomes in this formula than we do in this formula. Okay, so my next video will be me working some of these problems and explaining what this exclamation part means and stuff like that.